temps. Ouais, j'ai prévu de continuer le cours demain.
Okay, so move to geodynamics again with Maylis. Maylis, better if you present yourself.
Okay, yeah, I will do it. Yeah, so good afternoon. So for those who don't know me, my name is Maylis Landeau, and I'm going to present 3 lectures that will be on Earth formation. So you heard about it by Marc Chaussy-Don, I think, on Saturday, but I will take a point of view which is a little bit more from a fluid mechanics and physical point of view. So just before I go into the heart of the topic, a few words about myself and about, what I do. So I'm currently a postdoc in the University of Cambridge, and I will move in January in IPGP as a lecturer. And in my work, I basically use numerical simulations and experiments, so the tools of fluid mechanics, to understand the dynamics inside the Earth and other terrestrial planets. So during my PhD, I studied convection and dynamo action in the core in IPGP with Julien Aubert. And during my postdocs in Johns Hopkins and the University of Cambridge, I switched to lab experiments this time, and I studied Earth formation and core mantle differentiation. So I chose this topic for this set of lectures because it's quite a growing topic today. There are more and more data about it, mainly geochemical data. But we still don't understand well the physical process, so the dynamics of Earth formation. So it's a field that, in my view, needs more modeling and fluid mechanics modeling. So I'll try to convince you of that. So in those three lectures, I will follow this outline. So the first lecture, I will basically introduce the main concept on Earth accretion and differentiation. So you probably heard some of them on Saturday. You probably heard some of them in other lectures in your various grad and undergrad studies. But I just want to make sure we are talking about the same thing at the beginning. I will emphasize both. I will introduce the basic geochemical data that we have, but also the physical processes in that lecture. So that will be today and a bit of tomorrow. Then tomorrow, this second lecture will be on what we call dimensional analysis. So it's a big, nasty word to say something which is quite simple, which is just to, the question is how, when you deal with a large system at the deep Earth, how do you build a lab experiment that represents the system? So you have your lab with perhaps your 40 centimeter tank. How do you make that experiment relevant for the deep Earth? So we'll take the example of Earth formation, especially, but that will be the topic of this second lecture. And the third one will be more like a seminar type. So I will just show you some of my research on the topic. And also, before I go any further, if you have any question, or if something is not clear or anything, just interrupt me during the presentations, really. I would prefer it to be interactive rather than just me talking all the time. Okay, so let's start with Earth accretion and differentiation. So what do we call accretion? So it's just the process, the different steps, the different sequence of events that goes from dust particles to planetary system as we have today, like in the solar system. So how do you form, it's all the events that form the Earth until the Earth reaches its current mass, basically. And we think that most of the Earth's mass was accreted by successive impacts, collisions. And so the study of Earth accretion is the study of those impacts and those events that form the Earth. So here, for instance, you have like one simulation of a large impact. So we think that those impacts are representative of what formed the Earth. Yeah, I can play the movie again, actually. It's quite nice. So that's a typical like moon-forming impact that has been proposed for the moon. Okay, but I'm talking about the study of Earth accretion and Earth formation, but it's actually a field which is very young, because when you think about it, we know the age of the Earth for like, we don't know it for, we haven't known it for a long time. We know the age of the Earth precisely, not a long time ago, actually. And the first quantitative estimate of the age of the Earth was made by Kelvin in 1863. So what Kelvin did, so Kelvin came a few decades after Fourier formulated the heat equation. And so Kelvin had the bright idea to say, okay, let's apply that equation to the Earth to estimate the age of the Earth. So what he did is he supposed, so at the initial condition, he supposed that the Earth had a uniform temperature close to that of molten rocks, but I mean, it took 4,000 Celsius. And then he assumed that the surface of the Earth is at 0 degrees Celsius. And with those initial and boundary conditions, he solved that equation. And if you do that, you get that actually you form a thermal boundary layer where the gradient of temperature are very strong, and the thickness of that boundary layer will grow over time. Okay? So at time 1 million years, it's there, and 100 million years, it's there. And again, Kelvin came after the Industrial Revolution, and so at that time, there were a lot of mines, coal mines in the UK. And again, he had a good idea to say, okay, well, in mines, when we go down, we can see that the temperature increases. So let's take the estimation of the gradient of temperature in those mines, and let's fit it with my solution. So that's what he did, and he found that he can meet that gradient if it takes an age of 100 million years. So that's how he estimated the age of the Earth to be 100 million years. Again, that was in 1863. And that's what we thought was the age of the Earth at the time. So again, we don't know the age of the Earth for a long time. Another point I want to make is that there was very much debate at that time, actually, and quite a lot of fights between the school of Kelvin, like who are more from a physical point of view, and the geologists. The geologists didn't believe Kelvin at all. And they were actually right, but I would say not for the right reasons. And something that I think is still important to remember is that so although the estimate that Kelvin gave is wrong, it's really one of the first attempts to bring like physical consideration in the field of geology. So it's quite important, I think, for earth sciences. But anyway, so Kelvin was wrong, mainly because, as you know, there is radioactivity in the crust, and so the gradient in temperature in the crust is actually mainly driven by an equilibrium with radioactivity. And the age of the Earth is much longer than that. But we know that the age of the Earth is much longer than that, not since a long time ago. Of course, it came from radioactivity. And Claire Patterson was the first one to give a precise estimate of the age of the Earth, or actually the age of the solar system, I should say, because he dated meteorites. And he gave a value which is actually really close to the accurate one. He gave a value of 4.5 in this paper. Billion years, sorry. So that gives you the age of the solar system, but what about the Earth? And again, it's actually quite recently that we can differentiate between the age of the earliest minerals in the solar system and the age of the Earth. And since radiochronology, as Mathieu introduced this morning, we know that now we can differentiate between the age of the earliest meteorites and the age of the Earth, and we know that the Earth is of about 100 million years. So it took 100 million years to, it took 100 million years to form the Earth. So this age minus 100 million years. And so this is just to demonstrate that Earth formation is really a young field. I mean, it's only since the 80s and the 90s that we can say something quantitative actually about Earth formation, those 100 million years. So why is it important? Because that's this period of time that determine the initial temperature and composition for the core and the mantle. So the initial temperature of the mantle is going to control the convection in the mantle, and especially the early dynamics of the mantle, that Mathieu talked about this morning. It will also control the powering of the geodynamo. So if you want to understand the dynamics of the Earth today, you actually need to understand what happened during the formation of the Earth. Emergence of life. Yeah, I guess it's still worth to mention that we think like life emerged before 3.5 billion years ago, which is not super far away on that scale from the formation of the Earth. So if you want to understand the condition for Earth, for life to form, you need to understand what happens during the early Earth, basically. Okay, so what are we talking about when we talk about Earth formation? So we talk about how you go from a cloud of dust and gas that we call a nebula to a planetary system as a solar system today with planets that are very well organized with a core and a mantle. And so we know that first the cloud collapses into a disk where dust start to collide and form planets as we have today. But the big question is, how do you go from a uniform cloud, very uniform or more or less uniform in composition, actually it's not exactly true, but more or less, to a system which is very well organized with very well defined layers. So how do you go from there to there? What is the timing of those processes? What are the mechanisms? And can we predict the initial temperature and composition of the Earth? So where do the constraints come from? Because we are talking about something which is very, very far in space and time from us. So how can we say something quantitative about it? The main observations come from geochemistry. So isotopic data and extinct radioactivity tell you something about the timing, as we mentioned. But the composition of the core and the mantle also give you information, because when the core and the mantle differentiate, elements partition between the core and the mantle. And the partitioning of elements depend on pressure and temperature. So the composition of the core and the mantle will tell you something about the pressure and the temperature during core-mantle differentiation. So what are those constraints? Okay, so the first one comes from, as we were saying, like extinct radioactivity will give you the timing of accretion. So we saw already the principles of radiochronology this morning, so I won't go through that again. But for instance, hafnium tungsten is a good system to record core-mantle differentiation, mainly because it has two, or I should add a third one, I guess. Three nice properties. The first one is that hafnium and tungsten are refractory, so they won't evaporate in the gas, or they will stay in the solid part of the Earth. Hafnium is very lithophile, whereas tungsten is very siderophile. So tungsten will partition into the core, whereas hafnium will partition into the mantle. And the third one is that the half-time of the system is actually short enough and of the same order, I mean the right of order of magnitude that you expect for core-mantle differentiation, for Earth formation. So I won't go to the principle of radioactive dating again, since you saw it this morning. Something that Thurzó mentioned this morning is that we always rely on chondrites as a good reference for the global Earth. So that kind of meteorites that are undifferentiated meteorites that you probably heard of on Saturday. And so the principles is, basically here you have an isochron where you have the tungsten isotopic anomaly. Here, the Earth, the chondrites, you draw a line between the two, that's what we call the isochron, and the slope gives you the age where those two reservoirs form. So basically here it's like 30 million years. And you can do the same game with meteorites. So for instance, so we have chondrites, but there are also other types of meteorites. For instance, like iron meteorites, as this one. So for the story, I believe this is kind of the largest meteorites on the Earth. I think I'm not saying something wrong. And it's an iron meteorite. And meteorites like this one are dated and supposed to be formed within 1.5 million years of the first object in the solar system. So 1.5 is really short compared to the 100 million years it took to form the Earth. So it's important to realize that very early in the solar system, you had objects that were differentiated into a core and a mantle. And by the way, for the story, so here you see, so it's a very large meteorite, and actually there was no impact craters that is observed around this meteorite. And we don't really know why. And you can see that this meteorite is also very weird because it has a very flat shape. And again, we don't necessarily know why, and we don't know why this meteorite has not fragmented during the impact. On many other impact craters, you see that the impact was fragmented all over the place. This one is, stayed coherent as a very big object. So why is that the case? We don't really know. Yeah, so as a summary of radioactive dating, so what we know in terms of timescale, what do we know? So we know that the Earth formed more or less in 100 million years. We know that the first object in the solar system, object in the solar system differentiating within 1 million years, the age of most iron meteorites. Chondrites were probably formed in a few million years. And yeah, then it's a bit more complicated. But that gives you the main time scale to have in mind. Okay, what about the thermodynamic conditions now? So we can get some information about thermodynamic conditions from siderophile elements, as I was saying earlier. So the principles is that any element will partition between the core and the mantle. And you can measure that by what we call partition coefficient, which is, here in this case, the concentration in the metal phase divided by the concentration in the silicates. And this partition coefficient depends on pressure, temperature, oxygen fugacity, for instance. And so the idea is that in the meantime, you can compute the apparent partition coefficient for the Earth if you know the composition of the core and the mantle. So that's not really trivial already, but you can get a model for the composition of the core and the mantle. So for the mantle, basically you use rocks from the upper mantle, and for the core, you assume that chondrites are representative of the global Earth, and you subtract the composition of the mantle to estimate the composition of the core. But anyway, so you can obtain partition coefficient, like apparent partition coefficient in the Earth. And so so here you have abundances in the Earth's mantle for different elements. And in blue, you can concentrate on the blue dots that are for refractory elements, siderophile elements. And so the blue dots are the composition in the Earth's mantle, and the crosses here are the composition you would get if the core and the mantle equilibrated at low pressure, low temperature. And what you see is that for many of those elements, you have more siderophile elements in the mantle than what you would get at equilibrium at low pressure, at low temperature. So that's what we call the excess in siderophile elements of the Earth's mantle. And that's the strongest evidence to say that there has been some equilibration between core and mantle at high pressure, high temperature. And that's also one of the strongest evidence for the existence of magma ocean in the early Earth. So the common view that people have in mind about those scenarios are this one, where the Earth is formed from different impactors that bring some metal and silicates to the Earth. The metal go into the magma ocean and form droplets that will sediment in the magma ocean and form a metal pond at the bottom of the magma ocean. Then the metal pond can migrate and form diapirs until they migrate to the core because they are denser. And so here the idea is here you can have chemical equilibration between metal and silicates. And so the game is to say, okay, in that case, we can get the partition coefficient from high pressure, high temperature. We can get the partition coefficient as a function of temperature and pressure. Here you have an example of a sample from a diamond cell experiment from Fisher et al. 2015, and you see here quenched silicate melt, and here quenched liquid metal, which indicates that here this part of the silicate melted, and the idea is to measure the composition in this part and deduce partition coefficient. And they do that at different pressure and temperature. They fit their empirical their results with that law, and they find values for the coefficients A, B, and C, and so that they can describe the behavior, the partition coefficient as a function of pressure and temperature. And then the game is to say, okay, what are the pressures and the temperature that will give you a partition coefficient equal to the apparent partition coefficient of the Earth? Is that okay so far? Okay. No. So here you have an example for cobalt and nickel, but you can do it for any elements, like supposedly, siderophile elements, as long as they are refractory, and it works better for siderophile elements. So here you have example for nickel and cobalt. Of course, because you have 2 degrees of freedom, I mean, it's better to have more constraints. Otherwise, you will have only one parameter. I mean, if you have only one element, you will have only one of the 2 constraints on pressure and temperature. So you need at least 2 elements to have pressure and temperature, right? You can add more, and you just this zone will get narrower and narrower, and hopefully it's not going to switch somewhere else, because if you have no solution, then yeah. But anyway, so here you have results from Sieber et al. And Fischer et al. And they find pressures and temperatures. So temperature of the order of 3,000 Kelvin and pressures between 40 and 60 GPa. And so that corresponds to a magma ocean between 1,000 and 1,050 kilometers in depth. The square? Here? That's a good question. Yeah, they are outs, and like here you see, so that's not their data point. Probably. I should check. I can't remember what those are. Yeah, we'll check. Can tell you tomorrow. Okay, so far, the assumption that is made is that the entire core and the entire mantle equilibrates at a given time. So it's a single stage event, and with full equilibration at the bottom of the magma ocean. But this is not really physical, because from a physical point of view, there is no reason that the core and the mantle fully equilibrate at the pressure of the magma ocean. So what if you have only partial equilibration between the core and the mantle? So the first one of the first papers that introduced this concept was Roger et al. 2010, where basically they assumed that the Earth was formed from impactors that were differentiated, but this time, so the mantle of the impactor merged with the Earth, but the core of the impactor, only a fraction k of the core of the impactor equilibrates with the mantle, and the fraction 1 minus k merges directly with the core. And so if you do that, now you add a degree of freedom. So here you have the degree of equilibration k as a function of the time of Earth formation deduced from isotopic data. So hafnium tungsten here and uranium lead here. And what you see on this graph is that if you take hafnium tungsten, for instance, you see that, so if you have a degree of equilibration of 1, which is basically what people have assumed so far, so 1 corresponds to full equilibration, the entire mantle equilibrates with the core, you see that indeed you have an age, which is of about 20 million years here. But now if you don't know the degree of equilibration, you can basically have an age that goes to almost infinity. So you have no constraint on the timing of Earth formation anymore. So the point of this diagram is to say that to interpret the geochemical data correctly, you need to know the degree of chemical equilibration. And the degree of chemical equilibration is determined by physical processes, because it's determined by how much of the core mixes with how much of the mantle. So we are talking about physical processes here. Yeah, so that's one way to do it. So that's in that paper, yeah, that's what they suggest. So at one point, this is quite large still, but actually, I think I'm not sure I understood entirely why, but in this paper, John argued that it's not really the right way to see it, and that hafnium tungsten records more the early stage of Earth formation, and uranium lead like the last or late giant impact. Yes. Okay. Okay. Yes. Yeah, so they don't say exactly the same thing. Yes. Yes. Yeah, then you have to find other assumption. But at least what this tells you is that the degree of equilibration is larger than 0.4. Otherwise, hafnium tungsten goes Okay, so this is important for the timing, but also for pressure and temperature. And this is illustrated on this figure. So here you have the apparent partition coefficient in the earth, or actually no, the apparent partition coefficient for nickel, so concentration in the core to the concentration in the mantle, as a function of the depth of the magma ocean, so the pressure mainly. The black curve corresponds to what you get for a single event and a full equilibration of the core and the mantle. And so you see that this curve meets the composition of the Earth in red at this pressure. So if you follow this curve, you find a magma ocean 800 kilometers deep. However, the dotted curve here corresponds to another model where here basically they assume that the drops equilibrate with only layers of the magma ocean. So the drops of metal fall, but they equilibrate only with like layers at a given depth. So there is some memory in the mantle. And so in this case, they predict this curve. And you see that if you follow this model, you find a magma ocean depth of like 1 through like 1300 kilometers. So both of those physical models are not very relevant, but it's just to demonstrate that the interpretation you find really depends on the physics that you put in your model. So can we bring new constraints on the physics? That's the point of that I wanted to bring. So to interpret those data, we need to know more. We need to make assumptions about the physics. We saw that we need to know the partition coefficient that we know from high pressure, high temperature, or ab initio models. But we also need to know the degree of chemical equilibration that is going to depend on how much mixing you have between metal and silicates. And so it depends on fluid dynamics. So can we bring constraints on the fluid dynamics and on the degree of chemical equilibration? So basically the work I've been involved in is really to, the goal of the work I've been involved is really to better understand the fluid dynamics to determine the degree of chemical equilibration. Okay, so let's take a few minutes. And so here are different processes. Yeah, so now I'm going to switch basically on, we're going to look at that, the fluid dynamics of Earth formation. So here you have different fluid dynamics processes, accretion in the disk, so dynamics in the disk, impacts, large impacts, and metal silicate equilibration. As an exercise, can you try to estimate the length scale and the time scale that are involved in those processes, just in terms of order of magnitudes? It's just to try to think about what are the different length scales, so length scale here and time scale here that are relevant. So perhaps I can give you 2 or 3 minutes to think about that, or is that something you want to do, or is that just boring for you? No? Okay, so yeah, do it. So if you can work by yourself or with like a neighbor, perhaps 1 or 2 people, like groups of 1 or 2, and just think about what are the length scale and time scale. Size, like what is the reference size? It's just like order of magnitude, not something precise, but just to give you an idea of. C'est bon, tu les as? Allez, alors on va continuer. T'es un mauvais étudiant? C'est bon, ouais. Bon, de toute façon, on va discuter. Du coup, euh, alors, des idées? Allez, bon, on va commencer par, puisque normalement ça c'est le plus simple. L'accrétion dans le disque. Du coup, quelle est l'échelle caractéristique la plus grande? Oh, sorry. See, you started to speak. Yeah. I'm. Sorry, I switched in French. Yeah, exactly. Yeah, okay. Okay. So, yeah, it might happen. So, if that happens again, just raise your hand, and you know. I didn't realize I was switching in French. Okay. So, any ideas of the length scale and time scales? So, let's start by accretion in the disk. For instance, what is the largest scale? Yeah, so it's basically the size of the solar system, or if you are interested in terrestrial planets, it's going to be 1 AU, like the distance, or like a little bit more because you are interested in the asteroid belts. But yeah, so yeah, millions of kilometers and a little bit more if you want to take the entire solar system. So the time scale. How do you find the time scale? What we already discussed. So 100 million years, because the time scale of Earth formation. So what about impact? Did anybody, should I put the answer actually? Well, yeah, exactly. You all know. Yeah, but how do you find it? No, but why? So what's the time scale and the length scale for impacts? Like, an idea? Yeah, yeah, and the time scale. So time scale is a bit tricky. It depends. So do you know the typical like impact velocities that you can get by doing impacts? Yeah, kilometers per second. How would you find that if you don't know the answer to that? Any idea? Sorry? Yes, the escape velocity. Yes. So if you take the escape velocity, how does it get? So the escape velocity squared is going to evolve as g, gravitational constant, m, the mass of the target, so the largest of the two objects, divided by the radius of the largest of the two objects, if one is larger than the other, much larger than the other. So if you take that and you take the mass of the Earth, the radius of the Earth, you get something I think of like 8 kilometers per second, for instance. So now if you divide the time, you just divide the length, which is the radius of the target, divided by your velocity. Okay, and that will give you a time scale with those value of basically of less than 1 hour, but of the order of 1 hour. That's why I put like hours over there. So time scale for impacts is hours. It's just so that you realize it's like a super fast process. Sorry? Okay, yeah, equilibration. So that's the other process. That I'm talking about the large scale. That's the time, typical time for the large scale. The flow, the dynamics of the large scale flow after impacts. So it is very quick. Now, if you look at very small scale, so chemical equilibration, how do you compute the time scale and let's start, actually the length scale is the easiest to start with. Idea? Typical length scale for chemical equilibration. It's actually the right answer, but how do you get it? So you can take the diffusive length scale, right? Have you heard of diffusive length scale in the past? So just the square root of diffusion time, the time. Typical diffusion coefficients for composition are 10 times 10 to the minus 8 meters squared per second. You inject hours in there, and you find a length scale of actually less than 1 millimeter, 10 to the minus 4 meter. but it's just an order of magnitude, yeah. So it's about 1 millimeter. And the time scale, I mean, you can, for instance, take that and divide it by the velocity, and it gives you a very, very, very small time scale. So if I switch off that now, my point was just that you have processes that happen on a very wide range of length scale and time scales. And so that's why it makes it very difficult to study the physics of those stuff, because you can't possibly simulate all those mechanisms in a single experiment or simulations. You have too many length scale and time scale for that. And so that's why we study them individually, one after the other.
During large impacts,
Yes?
you have 1 hour, it's an hour with impact. It's even less.
Yeah.
Impact.
No, the impact. No, that's why I'm talking about the flow after the impact.
But the flow after an
The
impact,
crater
you
opening.
show?
Yeah, and that's about a few hours. Yes, that's a few hours. So maybe I should. Yeah.
So, for example, for moon formation,
Yeah.
it takes a few hours.
The moon. No, it takes more time to form the moon because we are going to see that later. Because then you have the moon need to reaccrete.
Yeah.
That takes more time. I'm talking really about the flow just after the impact in the largest object.
The crater flow.
Yeah, the impact cratering process. Yeah. Yes, and then the migration of the core to the, I mean, the core of the impactor to the core of the Earth. In liquid mantle, yes. We are going to discuss more of that tomorrow in the dimensional analysis stuff, but yes, it's actually a few hours as well. Okay, so let's study each of those processes now. Or study, we didn't say study. Right, let's see what are those processes. So accretion. So here are the main stages of accretion at the scale of the disk. So the cloud, the nebula collapses into a disk. In the disk, the dust coalesce to form planetesimals, kilometer-sized objects. When you have formed kilometer-sized objects, you know that gravitational interaction will be sufficient to induce collisions and merging between them. So you will grow planets that are bigger and bigger. Until you form planetary embryos. You form planetary embryos probably really fast, in 1 million years. But then it takes much more time to form Earth-sized planets. So probably 100 million years to go from a Mars-sized planet to an Earth-sized planet. And that involves very energetic collisions that we call giant impacts. So let's start by the first stage of accretion, that one. So how do you go from the nebula to kilometer-sized planetesimals? So first, the nebula collapses because of gravity, and it forms a disk. So do you have an idea why it forms a disk? Why does it have a disk shape? Go ahead. Tangent, yeah, so I guess I think you got the idea, but yeah. So perhaps a little bit more precise. No ideas? So it's actually because if you have some rotation, some angular momentum in the cloud initially, when it collapses, you conserve angular momentum. Angular momentum is going to write as the mass, or in simple system, mass times the velocity times the size of your system. We know that this is conserved. So if r, the size decreases, u has to increase. So I can write it I could write it like that as well, omega. So omega is a rotation rate times r squared. So r decreases, omega has to increase to compensate that. This is the ice skater, basically, that rotates faster when she reduces in size. So your disk is going to have more and more rotation. And because it has more rotation, the centrifugal force increases. And if you just do a sketch of that, can anybody see, or should I switch on the light? Is that fine? So if you start with a cloud like that, with a rotation axis here, the cloud rotates faster and faster. So if you take a particles here, the balance of force here, you will have the centrifugal force, but then gravity. So the sun will be here. It's very rough physical interpretation, but basically you have the sun here, so gravity goes that way. So the resultant of those two is going to go that way. So you have a force or a component of the force that is going to be perpendicular to the equator, and so your particles are going to actually sediment in the equatorial plane over time. So that's why you will form a disk. So mix of conservation of angular momentum and rotation. Okay, so now, how do you go from this disk of dust to kilometer-sized objects? So that's actually something that we don't really know the answer to the best of my knowledge. It's very debated. We don't have any clear, simple mechanism to go from dust to kilometer-sized objects. Those objects are actually too small for gravitational interaction to be effective. And so the main problem is that at this stage you also have gas, and so the gas in the disk impose a drag on each single solid particles. And because you have a drag, the particles will migrate inwards toward the sun over time. And this happens really fast, in probably 1,000 years. So you need a mechanism that accretes kilometer-sized objects in less than 1,000 years. I mean, this is really quick again. So what could be those mechanisms? So what has been proposed initially were gravitational instabilities. So it's a complicated word for something which is really simple. Again, if you have a layer of material here, or like here, I mean particles in that case, if you have some perturbation on that, for instance like this, those zones have more mass, and the zones that have more mass are going to attract more mass again, right? So there is an instability just due to that. So you will form, over time, you will form clumps of materials. That's what we call the gravitational instability. So can those instabilities be enough? The answer is like, not really, because for them to be fast enough, we need very high concentration in particles that are not very realistic. More recently, Johansen et al. 2007 proposed that actually turbulence could help, perhaps, to create denser regions, because region of high pressures actually have the tendency to condensate material particles. So you have more particles where you have higher pressures. That could help the mechanism of gravitational instabilities. Another mechanism that has been proposed by John Watlofer is actually if there is some ice layers on the dust, during a collision, you could have the ice could melt and solidify very quickly so that the particles stick together. So that's another mechanism. But again, they are not really very, it's not very clear that those stuff can work. That one perhaps is the most accepted one today. But once you have formed kilometer-sized bodies, then you are fine, because we know that gravitational interaction will be enough to explain the formation of terrestrial planets. So just successive collisions. To study that step, usually we use what we call n-body simulations. So you basically consider a number n of particles, and you solve the equations of motions for those n particles. And each time they collide, so each time their orbits come, cross, you assume that they merge and form a larger object. And like that, you can, grow bigger and bigger objects. Here you have an example of one of the results from one of those n-body simulations. So here, so basically those graphs go from 0, so time 0, to 10,000 years. So here you are going from, time is going that way. The y-axis is the eccentricity of the orbits, and the x-axis is the distance from the sun. So you start from this system where you have 2 planetary embryos and a number of planetesimals, and you look at how this system evolves over time. And you see that the planetary embryos grow over time. Their size here is proportional. I'm not sure it's proportional, but it's related to their mass. So they grow bigger and bigger. So just to give you an example of those tools that are used for this stage. And so here you have one type of results that you get from those simulations. Again, the mass divided by the mass of the Earth as a function of time. And the main result is that you have two stages of growth. The first one goes from kilometer-sized planetesimals to mass-sized embryos in a very short amount of time, probably 1 million years. But then to go from mass size to Earth size, it takes much more time, 10 to 100 million years, according to those simulations and body simulations. And that stage is more or less continuous, more like continuous process. But here you have a very stochastic process because, well, I shouldn't say stochastic, but you have a very catastrophic process. Because you see that actually this event, which probably accrete between 70 to 90% of the Earth's mass, occurs through very few events, so very few large impacts. So very few large impacts will actually accrete a lot of Earth's mass. Okay, yes, the grand tack. So there are a few characteristics of the solar system that those N-body simulations had trouble to explain for a long time. One characteristic is the size of Mars. The simulations I just showed you had a tendency to produce objects that were much larger than Mars is in reality. And also, they had trouble to explain the origin of water in the Earth. And that's something that has been solved by more recent simulations or scenarios that are called the Grand Tack scenario or the NIS model. Here it's 2012, not 21st. Anyway, I'm looking into the future. So their model is basically summarized here. So you start from planetesimals that are very dry in the inner solar system. Here are Jupiter and Saturn. And here you have water-rich planetesimals in the outer solar system, which is further away from the sun. And their idea is to say, okay, Jupiter and Saturn are going to migrate inwards because of the drag I was mentioning, because initially you have gas in the disk. But after some time, and so when they do that, they migrate inwards, they actually, you have like planetesimals that get scattered in the way because they are in the way of those big planets. And you start forming the asteroid belts, which starts to be formed of very dry asteroids. But then the gas in the disk goes away, and those planets do not migrate inward anymore. And actually, those models have shown that they start to resonate. So Saturn and Jupiter start to resonate, and that makes them move outwards in the solar system. It's a bit of magic I found initially when I saw that paper, but it's actually now quite an accepted scenario. And I shouldn't say that because this is recorded on YouTube. But anyway, so then they migrate outwards, and the asteroids that are water-rich are thrown in the asteroid belts. And you get an asteroid belt that have, both water-rich and water-poor asteroids, and in the right order compared to what is observed in the solar system. And most of all, you do produce a small Mars with that model. Okay, so that's it for the accretion, so for the scale of the disk. So what about impacts now? So as Philippe was saying, so giant impacts are important, first of all, because we think they are the most accepted scenario for the formation of the moon. So here is an example of the moon-forming impact that was showing at the beginning. And yeah, so that the timescale here is hours. But the point is to actually, so here you see that you have the embryo that impacted the Earth. It re-impacted it here. And you see that you have materials that get ejected away from the Earth. And if it's far away, it's out of the attraction of the Earth, and basically it will, so those materials here will recoalesce to form the moon. But they will recoalesce on a longer time scale. That's the idea. So there are still few problems with the standard. So the standard model for Earth formation is an impact with a mass-sized impactor on the left here. However, there are troubles with this model because it difficulty explains a few features. The first one is the angular momentum between the Earth and the Moon. And the second one is the isotopic similarities between the Moon and the Earth. It's really incredible how the Earth and the Moon are similar in some isotopes. And any moon-forming scenario needs to explain that. Two more recent scenarios that have been that can actually meet this constraint are those ones. So the fast-spinning impactor, so an impact with a very fast-spinning impactor, actually has shown. I mean, the Chuck and Stewart have shown that it can send material mainly from the Earth's mantle, and in that case, you form the Moon from the Earth's mantle, which would explain why it's very similar to the Earth. And that one, where basically you have an impactor that have a size very similar to that of the Earth. In that case, because the impact is symmetric, all you send far away is basically a mix of both, but an equal mixture as the mixture of the final body as well. So that's why it will have the same isotopic ratio as the mantle. Yes? Fast-spinning impactor, I think. Right? No? Earth? I should check. Okay, and there's something else to check tomorrow. Should check tomorrow then. We'll check that as well. But anyway, so the problem, so the problem with the fast-spinning scenario and the equal size impactors is that they produce an angular momentum which is much higher than the angular momentum of the Earth and the Moon, and so you need a post-impact mechanism to explain the dissipation. So it's not entirely satisfactory either. So today we don't have a very simple moon-forming impact that could explain both of those information of those constraints without any other mechanism. So one scenario that could explain that, which has been proposed very recently by Locke et al., so Simon Locke, in 2000, actually this year, is like the principle of what they call synestia, which is basically a scenario where the moon-forming impact is so energetic that you vaporize and you melt much of the Earth's mass and the impactor, and you form a structure that they call synestia, which is basically something that has the form of a disc shape, and where the Moon would accrete but as condensation of material, so solidification of material within this disc, rather than like solid material being injected during the impact. So another reason why impacts are important is for heating and melting. If you want to know the initial temperature of the Earth, you need to know how much heating you got from the impact that formed the Earth. So this is something which is summarized here. So it's a bit of a complicated diagram, so we can go through it together step by step. So you have the increase in temperature as a function of the mass of the largest object, so let's say the proto-Earth. And the black curves, so the solid curves, are the heating you would get from impacts if you assume that the kinetic energy of the impact is converted into it. Okay, so you take the escape velocity that gives you kinetic energy, and you suppose that it's converted into heat in new formed objects, and you get a scaling law that follow those lines. And this is going to depend on the size of the of the impactor as well. So gamma is the ratio between the size of the impactor to the Earth. So if you have a large impactor, you get more heating, and if you have a small one, you get less heating. But an important parameter is the size actually of the proto-Earth. And you see that, in red, you see the line that corresponds to like 1000 Kelvin, So above this line, basically, you expect widespread melting. So you see that to get widespread melting, you need two conditions. You need the proto-Earth to be quite big, actually. It works only if the proto-Earth is big enough. And you need the impactor also to be quite big, so at least 10% of the proto-Earth's mass. So that's really what we call the giant impact. So melting by impact will be efficient only for planetary embryos for the late stage of Earth accretion. Now, the dotted line corresponds to heating that you get from radioactivity from short-lived isotopes as iron 60, I believe, and aluminum 26. I think I'm correct. Yeah, aluminum 26 and iron 60 as the short-lived isotopes that like radioactivity in the early. Yes. Yes. Yeah, iron 60. Yeah. Okay. So and in that case, it depends a little bit more less about on the mass of the planet, but mainly on the time at which the object accreted. Because if it accretes very early, then you have still a lot of radio active elements or isotopes left. If it accretes later, you already have no radiogenic elements, and so you have no radioactive heating. So if it accretes at 0 million years, you get a lot of heating, but it accretes at 4 million years, it's too late, and there is no melting by radioactivity anymore. And so what you see here is that for planetesimals, radioactive heating can be actually enough this time to induce melting. So as a summary of this graph, for the early stage of accretion for planetesimals, heating and melting will be dominated by radioactive decay, by radioactivity. And for the late stage of accretion, for planetary embryos, it will be dominated by impacts, because you can see that those lines are actually much higher than those ones. Yes. Okay, so actually that's all for today. That goes on time. So tomorrow we'll talk about metal silicate differentiation. So the third one. If you have any question also.